right. So boosh. All right. So, oh, it didn't save. Wait, tap the brakes. I made it look better. I didn't like the lime green 1980 VW red. So I made it my forest green. No, that's literally my first car. Yeah. Diesel, 4 on the floor. Oh, sweet ride. It was such a sweet ride. Except no air conditioning, no power windows, 2 speakers, just 2 in the front, and they were like this big. Yeah. Oh yeah. Oh yeah. Hatchback. Oh, good times. Great. Then my mom had to drive it one day. Blew the head gasket. Sad. Schmeling drove. I don't even know what is that. Is that the Dodge something? Dodge Stratus? Is that a Dodge Stratus?
Probably.
Big time stuff. Okay. And Kay Hill. We'll learn about Kay Hill's first car a little bit later on today. But yeah, she had a Pinto, which keep off my rear. I'm explosive. It's true because the gas tank was right in front of the rear bumpers on the old Pintos. And so if they got rear-ended, they would explode. Allegedly, that's bad. They say. So today we're going to have notes on exponential modeling. You are going to be on your own, or I should say on your own. You're going to be in your own notebooks. We are not in the note sheet. However, I do draw your attention to said note sheet because you will need that note sheet this weekend when you watch. You'll have a video to watch this weekend on your own before class on Tuesday. Okay? Okay? Here we go. So, quick warm-up here for you today. If you would be so kind as to graph and give me at least 2 key points on these 2 exponential functions, please. Alright, so if I had to pick 2 key points for this first one, I would pick an x value of -4. If I do that, then I get a y value of 2, so I would go through the point -4, 2. If I were to pick another one, I would pick -3, and I would go through 6. Agree with me on those 2 key points. The graph of this exponential function would look like that. It'd be sharp, it'd be pushed off to the left, because at 0, I would need to be at 162 up on my x or on my y-axis. Yes, ma'am.
I thought we were always supposed to do 0 and 1 in the graph.
So we want the exponent equal to 0 and exponent equal to 1. Yes. So that we don't have 162 and 500, 487, 86. Those 2. Yep. Yep. Over here, I would choose my 2 key points. Oops, I forgot to put my horizontal asymptote on this graph. I forgot that I was going to say that when your horizontal asymptote is in axes, or if your vertical asymptote is in axes, you can always do dashes like that so that you can actually see it on here. That is what your horizontal asymptote is. Okay? Over here on this one then, I would choose 0 as my first x value. And when I plug in 0, I get e to the 0 is 0, or excuse me, e to the 0 power is 1, minus 2 is -1. There for that one. Then I would choose -1. plug in. If I choose -1 as an exponent, then I've got e to the first power, which is 2.719-ish, minus 2 would be 0.719-ish. Okay? So when I graph this, I have a horizontal asymptote at -2. I go through the point 0, -1, and I go through this point up there. So then this comes down through here. Oops, I missed both of them. You didn't see that, but I missed them. Oh, my lance eye, scroosh. Scroosh! I did too much erasing. There you go. Yes? Love it. Good stuff. So, we're going to talk today about modeling different scenarios, different situations. So, let's suppose it's soon to be the fall. The leaves are turning. When I look out this way, the leaves aren't as turning, but when I look out this way over here, the leaves are turning more and more and more in this block over in this way. At one point in time, I watched from 2 doors down, I watched a hot air balloon hit a house.
What?
Day in class. Yeah. It was kind of crazy. Because I'm sitting here and I'm teaching. It was in, what is it, 2 doors down. I was watching. I'm like, hey, there's a hot air balloon out there. All the kids look, oh yeah, pretty neat, pretty cool. And I move on teaching. And then all of a sudden, hot air balloons it was trying to land on the football field. And it missed. It came up a little short and it just clipped the corner of the house. And I laughed. That's kind of funny. Kids had no clue what was going on. I just want to hit the house. Alright, so we're suppose you go outside, you rake your yard. So let's say you go outside, you rake your yard. Okay? So then you take the rake, and you go into the garage, and you're going to hang your rake, because you always put your tools. And you always put your tools back where you got it, because then the next person knows where to get them. Okay? So you go back, you hang up your rake, you turn around, biscuits and gravy, there's 50 leaves laying on your yard. Now you get 2 choices. You could say, not on my watch, and you go back out and you rake those 50 leaves, or you say, I'll deal with that. Well, you're going to choose the latter. You're going to deal with that later. Okay? So then you come back an hour, you get yourself a nice, sandwich and a nice something to drink, maybe a bag of chips or a plate of chips or something like that. You gotta re-energize the body after working so hard raking leaves. And you look out, now there's 8% more leaves out there. And you say to yourself, how do we know it's 8%? We just make it. Okay? You probably counted out how many leaves there are on the ground. So after 1 hour, my question to you is this. How many leaves are laying on the ground after 1 hour if there was an 8% increase in the amount of leaves on the ground? 54. Now, give me one method to get 54. Just wait, I already heard yours. I don't want to hear yours. I want yours second. That's the way that I want to follow. So that's why I want to go second. Anybody? Maybe we only all did it the one way. Okay. One way is to multiply 50 by 8%, which 8% in the decimal is 0.08. If I do that, I get 4. Then I got to add 50 to that, and I get 54. Okay? That's the long way of doing it. Now, my dear, what do you got?
That is 50 times 1.08.
Why did you do 1.08?
Because it's increasing.
Yep.
And the percent of 8%.
The 1 gets me the 50, and then the 8 gives me the 8% increase. Yep. Okay, exactly. Okay. So this number here represents 50, times 1.08%. Or 1.08, I should say. Now, 2 hours later, now you started watching Suits. I'll go with Suits because Krug's is binge watching Suits right now. Yeah, of course he is. Okay, so let's say because Suits is about an hour long. Okay, so you watch an episode of Suits. Okay, right? Now it's an hour later. You've gotten your sandwich. You're full. Your tummy. You got that warm feeling inside because your food's digesting and the tummy comes. And then it's an hour later. You're done watching Suits. How many leaves are on the ground now? Talk to me. How many leaves on the ground right now as we speak?
It's like the age. That doesn't make sense.
What do we got? Let's round to the tenths because we wouldn't round to the tenths normally because I would just consider we'd round up because the 0.32 should be just an extra leaf because we could have 0.32 of a leaf, but we don't in this case. So let's say, what do we got here? How many leaves? 58.3. How do we come up with 58.3? We went with times 54, right? But 54 we already said was 50 times 1.08. So then you multiply that by another 1.08. Ooh, can we do that? No, that we can't do. Okay?
But I got the same answer.
You got 50. You got 58.32.
Now I got 58.
That's why you got 58, and I got 58.32. No, it did not. Okay. No, you're going up by 16% in 1 hour. Going up by 16% is not going up by 8% over 2 hours. So no, you cannot do it that way. Okay? Now, you're like, I am into Suits. Another episode of Suits. Down in through the eye holes and ear holes and into the brain. Okay? So now, 3 hours later, how many leaves are on the ground?
63.
63? Still rounding to 10, a tenth?
I think.
63.0? Yep. I couldn't remember what it was. Good job. Okay, couldn't remember. All right. 63.0? Okay. See, now here, say yours would have been only 62. Right? So now we're off already. We're off by 0.3 here, now we're off by a whole 1. So if you want to be off, you keep doing it your way. Okay? So my question to you now is, this is getting kind of repetitive, right?
Yeah.
So if we say n hours, so if we go for n hours, okay, we're just going to say n is our hours, okay? What would our exponential function over here be?
1.08 n power.
To the n power in this case, yep. So we'd have 50 here times 1.08 to the n power, right? Now that's going to make it easier for us to do what the question is actually asking. The question is asking, find the number of leaves on the ground 12 hours after you've been binge watching Suits for 12 straight hours. Okay? So how many leaves are on the ground now? 12 hours later.
Yeah, so I just did. Wait, I have a question. So I did this like early, like, but I did n -1.
Okay?
Like, what is the difference between when you should use n and then n
Well, see, if I use n minus 1, then I'm always 1, then I gotta go to 13 out.
Yeah.
It's when
Yeah.
you don't start with
Yeah.
0.
When you don't start with 0, then it's an n minus 1, but we started with 0. Yep. Yep. And we'll usually have, in exponentials, you're usually given that a value. What do we got for total number of leaves on the ground? Again, rounding to the tenths. 125.9 leaves. That's a lot of leaves. Okay? Love it. Now, if our population, and we say population here, and it's a very loose term of population, because population could be many different things. Population could be spores in a petri dish. Population could be the value of a vehicle or the value of an object. Population could literally be the population of a city. Okay? Population could be a number of leaves that are on the ground. Okay? So population can be many different things here. Okay? So if it's changing at a constant percentage rate, not changing at a constant rate, changing at a percentage, it's always growing by a percentage. When you were doing yours before, you were changing at a constant rate. You were doing a linear function. You weren't doing an exponential function. Okay? So we have to follow this one. P sub 0, that's our initial, that's our first, that's our starting, that's our 0, plug in 0 value. Okay? 1 plus if we're increasing. 1 minus if we're decreasing. Because that B value has to be bigger than 1 if we're in exponential growth, less than 1 if we are exponential. Okay? So plus or minus there. R is our rate, but we have to convert our rate percentage to a decimal. Remember, slide twice. All right? And T is time in years. All right? Love it. So with that being said, in that function, please come up with an exponential function with an initial value of 12, and it's increasing at a rate of 3.5% per year. Then, underneath here is my favorite pre-calculus example of the
No, you're not.
Every day.
No, you
All right.
like this side, bro.
So,
Try.
P of T is going to be, initial value is 12 times 1. Are we increasing or are we decreasing?
Increasing.
Increasing, so that's plus. So that's going to be 1.035 to the T power. Do we all agree with that? Oh, let's do it. Here we go. You purchased a slick 1979 Ford Pinto back in the year 1985. You and Marty McFly purchased that bad boy. And it was valued at $1,800. Your dad ran a construction company, funded you some money, you got yourself this classic Pinto. White with cherry red striping, Starsky and Hutch style. Those of you that don't know, Starsky and Hutch was a show back in the 80s. They drove a Ford, I forget what the Ford was, but they drove, and their car was red, but then they had this like slick racing stripe on it, and that was white. Okay? It was all the talk of Greenway High School in North Duluth. Oh, you were the cat. Okay? Right? Hard to believe, but somehow this hot rod actually lost value at a rate of 7% each year. Okay? Now, for those of you in the back that can't really see the old grainy 1985 photo, but that is one and only Trig Mama in front of said Pinto. Okay? Alright? That's That's her actual Twitter.
Really?
Really. Okay. You find me the exponential function 1. You're finding me the exponential function that describes the value of this classic car. Okay? 2, you're finding me this hot rod's value in the year 1990. Okay? Go. So, your function, let's call it P for Pinto, of T for time, is going to be, or it should have been, 1800 times 0.93 to the T power, right? Because we're decreasing in value 7%, so it's 1 minus 0.07, which is 0.93. What T value are we finding? 5. 5 years after 1985 is 1990. Yeah. Should be worth $1,250. Oh, $52, not $53. $52.24. Priceless today. Okay? Well, they don't make things feel like you can't. I mean, you can't find a bid.
How are cars that cheap?
Like back then?
Yeah.
Yeah.
That's like so cheap.
I'm not gonna lie to you. So that rabbit that my parents bought, that was maybe $5,000 back in 1980 for a brand new car, 0 miles. Yeah. Because we're mean. Okay. Again, it's not in your notes. You're in your notes today by yourself. I get it. Okay. Mistakes happen. I mean, it's smelling, for God's sakes. Okay? So, suppose the population of San Jose is following an exponential growth pattern. In 1990, the population of San Jose was approximately 782,000 people. In 2000, it grew to approximately 895,000. Okay? So based off of that, I want you to give me 2 ordered pairs that will be on our function, in our graph, data points, if you will. 2 of them, please.
Is it 1990?
Hold on. Sadie, what are you talking? Give it to me. Walk me through it. Start your question again. I know, but I want, because I know what you're going with, and I want to talk about it. 100% we got to use the numbers that they gave us. That's why they gave us the numbers, right? Okay? So what kind of data points can we make out of this one? What do you got, Addie?
I would start by
Like year 0? Okay.
I would just do 782.
And then, okay.
Say like 80,000.
Bingo. So we got it. So if we do that, which is great because now our numbers are a heck of a lot smaller, right? Okay? So if we do that, then our T value here is going to be years since 1990. Yep. Right? And if we do that, then our P is going to be population in thousands. Because we dropped off the 3 zeros at the end. Okay? If that's the case, and I love that because our numbers are smaller. Now, could have we still gone with 1990 and 782,000, which Sadie was going to, that was the question that she had actually asked. Okay? Yeah, we could have. Our numbers aren't going to be as nice. Okay? But we could still do that. Okay? So if that's the case, what would my second data point be? 10, 895. Okay. Now, we need to think back to Algebra 2, and we need to come up with an exponential model for this scenario, for this exact situation. Okay? We can do that because we are limiting ourselves to this type of function right there. A times b to the t power. Okay? Where t is the time in years, and a represents the initial population at t equals 0. Well, because Addie said that we're going to make 1990 be year 0, what is our a value then? 782. Just 782 would be our a value then. Then we can use the other one. 895 would be our population value. 782 is our A value. We don't know what our B value is, but we know that T is 10 for our population to be 895,000. What I would like you to do now is I would like you to solve this for B. Round it to 4 decimal places. Yep. No, close. No. So what do you do first? What do we do first if we want to solve for B? Do we subtract? Do we subtract? No. What do? We divide by 782 because it's being multiplied.
You are a goober. I think I have the answer.
So that's equal to b to the 10th power. Now what do? We have to take it to the 10th root. So we have two options here. We could take it to the 10th root, or we could take it to the 1/10th power. Either one of those will get us the exact same answer. Rounded to 4 decimal places is 1.0136. Should be a 3.6. Then you rounded somewhere earlier than me. I don't round ever until the very end. Never round. Yep. Okay. So my answer, my equation here then would be 782 times 1.0136 to the t power for my function.
So it's increasing by 1.3%.
1.36% per year. Yep, exactly. Okay. So using that now, approximate for me the size of San Jose's population in the year 2005.
15, right?
What year am I using? I'm using the 15th year, so I'm looking for P of 15. And if I plug in that, I get 957,483.
What I get? No.
Talk to me.
It's just because I used the equated.
You used the rounded one,
Yeah.
and I didn't. Yep, so you should get 648 then.
I just got sig fig.
Okay? You didn't get sig fig. You got exact versus rounded.
Yeah.
That's not sig fig.
So what is sig fig?
Sig fig means significant figures. That means your answer can only have a certain amount of specific digits. Okay? So let's graph this, and the key part is we need to label our axes with words. So let's go on to our graph. Let's create ourselves a new graph. If I graph this scenario, I would have 782 times 1.0136 raised to the, I've got to switch it to an x here because I'm in a function of x, not a function of t. When I hit enter, I don't see it. Because my window is way too far in. So let's come up with a window that we can zoom it out to. Menu, window settings. Window zoom, window settings. X's is time, right? Okay. So we needed to go out to at least 15, right? Okay. So let's go out to 20. I'm going to go by 5s. Y is our population, right? We started at 782. So we got to at least have 782 somewhere in there. But let's go up even higher. So what do you want to go with? 1,000. Okay. So let's start. So for me, because I like to see my axes, I'm going to go here, negative 100. And I'm going to go up to 1,200 by 100. Okay? So there is it's not very steeply growing, right? Okay? So when I come back here to sketch my graph, it's more of a flatter type growing, yet still growing type of a graph. The kicker is the direction said we need to label our function or our graph with words. So over here, I would say that this is population in thousands. Down here, I would say this is time in years since 1990. Yes, ma'am. How do I know what to put? Because that's literally what we graphed, because that's how we described our variables way back. Because it's an exponential function. Right? Because the variable's in the exponent. And I know it's curved up because the b value is bigger than 1. All that stuff that we learned yesterday. Okay? If it were y equals mx plus b, then it would be flat and be a line. It's not. Okay? All right? Now, here's the kicker. Last question. Assuming that the population continues to grow according to this model, approximately what year did the population surpass 1 million? Well, now we can go to our graph. Here, remember that our population was in thousands. So what would we input for a million? We'd input  1,000 for our million. So we can hit tab, And after we hit tab, we can graph the line 1,000. That is then, because our graph is in thousands on that one, we can graph this, and that is our 1 million line. So what would we then be looking for? An intersection. Menu. Analyze graph. Intersection.
Why is it in this weird
Yep. Okay. So my question to you now is this. When does the population,
Mine says 1 plus 3.
because you're rounding too short. If you hover over it, it'll tell you what it is. Hover your. When does the population surpass 1 million? So we started at January 1 in 1990, right? So wouldn't it be 2008, during 2008?
Yeah.
Because 18 would get me to January 1 of 2008, right?
Yes.
Okay? So let's say February or March-ish. Of 2008. Agree? Good times.